In section 6.5, we look at periodic variations in element properties. It seems kind of obvious that if the properties of an atom are determined by its electron configuration, and if the electron configurations of the elements in the periodic table vary in a systematic fashion, then the properties of elements should vary systematically across the periodic table. We're going to be looking at three properties. We're going to be looking at radii of both atoms and ions. We're going to be looking at a property called ionization energy. And finally, we're going to be looking at a property called electron affinity. So, by the end of this video, you should know how those properties vary across the periodic table. As I mentioned in the introduction, as electron configuration varies in a periodic fashion, we would expect to observe that many properties of elements vary in a periodic fashion as well. The first property that we're going to be looking at is atomic size, or what we might say atomic radii. Now, it's important to realize that atoms are not hard spheres. And so typically when we determine the diameter of an atom, we're going to do so by measuring the distance between the atom and a neighboring atom. So this is going to depend on what the type of compound and the type of neighboring atom. So you will see variations in the size of a given atom depending on how the size of the atom was determined. That being said, the trends should be the same regardless of an absolute value for an atomic radii. So typical ways that folks will measure the radius of an atom is by measuring the distance between two adjacent atoms in a covalent compound. If the element exists as a crystalline solid, like most metals, in fact all metals except for mercury exist as crystalline solids, then we can define the metallic radius, which will be half the distance between two neighboring atoms in a metal's crystal. Sometimes we'll determine the ionic radius, and to do this we'll use a technique called X-ray crystallography, and this is going to be the distance between adjacent atoms in an ionic compound, and we'll need to do some fancy measurements, and we'll learn how to do those later on in chapter 10 to get the actual size of the ions. As we go down a group in the periodic table, the value of the principal quantum number increases. That is, in period 1 of the periodic table, we're putting electrons into the first shell. In period 2 of the periodic table, we add a second shell of electrons. In period 3, we add another shell of electrons. So it's not surprising that as we go down a group, atomic radii increases. As we move across a period, we're adding electrons to the same shell. So they're going in at approximately the same distance from the nucleus. However, as we move left to right across a period, the number of protons present in the nucleus of the atom increases. So we're putting electrons in at about the same distance from the nucleus, but we're increasing the charge on the nucleus. This is going to suck those electrons towards the nucleus, which is positively charged. And so what we see as we move across a period is a slight decrease in atomic radii left to right. Now that trend is minimal compared to the up-down trend, but it's definitely present. So a typical question would be to rank atoms in order of increasing atomic radii. So we want to look at our periodic table to do this. Sodium's in group 1A, period 3. Potassium's also in group 1A, but it's in period 4. Chlorine is in group 7A in period 3, and argon comes after chlorine. So the elements that are in the third row of the periodic table are going to be smaller than the elements that are in the fourth row. So we recognize that. So sodium, chlorine, and argon are going to be smaller than potassium. Now, how does the trend vary across the third period? Well, the elements will decrease in atomic radii. So, in order of increasing radii, I would go argon, chlorine, sodium, potassium. So that's it, really, right? That's it, just using our little trend there. Argon, chlorine, sodium, potassium. We just got to be careful not to get confused. Now, ionic radii of an ion is determined from measurements on a crystalline ionic solid. There are some general trends for ionic radii. Cations are formed by removing electrons from an atom, so they're going to be smaller than the atoms that they are made from. Anions are formed by adding one or more electrons to an atom, so they're going to be bigger than the atoms that they are made from. We still want to keep in mind the other trends that we talked about. In general, ionic size is going to increase down a group, and in general, ionic size is going to decrease as we move left to right across the periodic table. So, across a period, ionic radii is typically smallest for the cations in that period and will decrease as we move left to right, and it will be largest for the anions in that period and will decrease as we move left to right. So let's look at row 2 of the periodic table, and you can see that the two cations there, lithium and beryllium, are smaller than the two anions that are indicated. So in any given row, the anions are always going to be bigger than the cations. However, we see that the cations decrease in size as we move left to right, and so do the anions. And that trend is repeated again and again and again. If we go to period 3 and we look at these three cations, you can see that they are smaller than the anions in that period, but both the anions and the cations get smaller as we move left to right. So it's almost like we've got two sequences within the one period, one for the cations and one for the anions. But the cations are always significantly smaller than the anions that are in the same period. So our second periodic property that we wanted to look at is the ionization energy, often abbreviated IE. And what this represents is the energy needed to remove 1 mole of electrons from 1 mole of atoms that are in the gas phase. So every element will have an ionization energy. We'll often talk about the first ionization energy, which we will give the abbreviation IE1. This is the energy required to remove the outermost electron, that is the last one in an atom's electron configuration, the one that is easiest to remove. So we're always working with a gas phase atom. We're going to take away 1 electron, giving us the single positively charged cation, and the energy required to do that is called IE1. Similarly, we can define the second, third, fourth ionization energy, etc. We normally abbreviate those in a similar manner to IE1. So the second ionization energy removes the second electron. So we're going to be starting with the singly positively charged cation in the gas phase, and we're going to be removing another electron, and the energy required to do that is called IE2. Now, a couple of things to note. The second electron is going to be being removed from a single positively charged cation. So that cation is going to attract the electron quite strongly. So it's always going to be more difficult to remove than the first electron, where we were attempting to remove the electron from a neutral atom. That is, IE2 is always greater than IE1. So we want to keep in mind that the closer electrons are to the positively charged nucleus, the tougher they are to remove. So what this means is that as we go up a group and right to left, my mistake, left to right across a period, atoms get smaller, therefore IE1 will increase. So IE1 is going to increase as we head to the top right corner of the periodic table. So just summarizing, IE1 will get smaller as we go down a group, or it will increase as we go up a group, and IE1 will increase as we go across a period because the atoms get smaller as we go across a period. So smaller atoms equals bigger IE1. So here's a little graph where we show atomic number versus first ionization energy. And this is us heading across row 2 of the periodic table. And you can see as we head across lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, IE1 increases. And that makes sense because the atoms get smaller as we head left to right across a period. Now let's look what happens as we go down a group. So let's go down the noble gases. There they are. And you can see what the trend is as we go down group 8A there. The ionization energy 1 gets smaller because as we go down a group, the atoms get bigger. Now, it is worth noting that we do see some spots where we seem to be bucking the trend, don't we? Right? Particularly obvious in rows 2 and 3 there, that we have some consistent exceptions. So to understand those exceptions, we need to think about what we call orbital penetration. So electrons in an S subshell spend a lot of time very close to the nucleus. If we look at the electron distribution, the radial probability distribution, we can see that the 2s penetrates closer to the nucleus than the 2p. And so what this means is that the 2s electrons and s electrons in general are going to be quite tough to remove in comparison to p electrons that are in the same shell. So we see this when we look at ionization energy 1 as we move across period 2. What we see is that the IE1 for removing the first p electron is actually smaller than IE1 for removing the previous s electron. There's a little dip there, right? And we see that kind of repeated consistently, that these p electrons are a little easier to remove than what we're expecting. Okay, so once we get sort of beyond the fourth row, less so, or we stop seeing the trend. But for rows 1 through 3, it's very obvious that the p electron is a little easier to remove than what we might expect. Now, these are sort of like minor details is powerful evidence that Schrodinger's quantum theory is actually working. Now, another little exception that we'll see is we get a little dip when we get halfway across what we call the p block. That is, the p4 electron is easier to remove than what we're expecting. Or another way of looking at that is that the p3 electron is slightly tougher to remove than what might be expected. And the reason for that is this: a half-filled p subshell is an especially favorable electron configuration, and so as a result, it's a little bit easier than what we're anticipating to remove that fourth p electron. Okay, so it's kind of tough to break this up, right? This half-filled p subshell. So that's something to keep in mind. That's the origin of those exceptions that we see in that graph of first ionization energy versus atomic number. Now, as we pointed out, successive ionization energies will increase. The reason for that is because it becomes harder and harder to remove an electron from an increasingly positively charged ion. In particular, what we'll see is if we look at a series of ionization energies, we'll observe that once we remove all of the outer or the valence electrons, there's a really large jump in ionization energy because now we're having to remove core electrons, which involves disrupting a very, very stable noble gas electron configuration. So I'll show you some data that illustrates this. If I look at the element sodium, sodium's in group 1a, so it has one valence electron. And you can see that the electrons that come after, that are removed after the first electron are really, really tough to remove. If I go to silicon, silicon is in group 4a and has 4 valence electrons. As we remove each of these valence electrons, we see a modest increase in the ionization energy. However, once we try to remove a core electron, we see a massive jump in the ionization energy. And in fact, what we'll find is that chemical processes do not mess or do not remove core electrons because the energy required is too high. That is, in a chemical reaction, an ion will not form that requires the loss of core electrons because chemical reactions cannot provide that amount of energy. The final periodic property that we're going to look at is the electron affinity, and the electron affinity is abbreviated with the letters uppercase E and A, and what it represents is the energy change when 1 mole of electrons is added to 1 mole of atoms, with everything being in the gas phase. So what we're talking about is taking the neutral atom and adding 1 electron to it to form the singly negatively charged anion. And the energy required to do that is called EA1. In general, because we're forming a bond between the electron and the atom, energy is released when the electron is added. So this will be a gain of, this will be a loss of energy by the ion. Okay. So there's a little bit more variation in electron affinities than what we see for ionization energies. However, the general rule of thumb is this, that the electron affinity increases as we move from francium up towards fluorine. And that makes sense because non-metals, those shown in blue here, they love to gain electrons, and metals, those shown in yellow there, they love to lose electrons. Sorry about the alarm going off there. Okay, so that concludes the video for section 6.5, and I hope you found it helpful.